flange beam has a dimension shown in the figure below. If it is subjected to a moment M of 260 kilonewton meters, part A, plot the normal stress distribution acting over the beam's cross-sectional area, and part B, determine the bending moment that's resisted by the flanges. So this is another typical problem for a structural engineer or for a civil engineer working with an I-shaped section. There is a typo there. That shouldn't be shear. That should in fact be, whoops, didn't mean to move that. That should in fact be bending moment. The pen isn't as responsive in Acrobat as it is in other sources. So yeah, this problem, we'll work it again when we get to talk about shear, and so I had a copy paste error. Apologies for that. So the point of this problem is first to plot the distribution of bending stress, and then figure out how much of the bending moment is carried by the flanges in the cross section versus the bending moment that's carried by the web of the cross section. Okay, so here we are in OneNote, and the first thing that I'll point out is to make sure that we're all on the same page with our notation. So these elements here and here are the flanges of the cross section. So we have a top flange and a bottom flange in this case. This element here in the middle is what we refer to as the web, the piece that goes in between the two flanges. So when we refer to the flanges and the web, then that is what we're talking about in this particular example. Okay, so the next step is I'm going to sketch this problem out, and I'm going to look at it in cross-section so that we can calculate the section properties that we need to do our calculations. So here I've gone ahead and sketched it a little bit earlier. So if we go in and put the dimensions on here, we have a breadth here of 300 millimeters, like that. The flange has a thickness of 20 millimeters. So flange here has a thickness of 20 millimeters. And then we also have the depth of the web. So this distance here is 200 millimeters over the full depth. This is 20 millimeters there for thickness, and I'll just leave the units off those. And then here the thickness of the web is 15 millimeters. So it's a doubly symmetric cross section. So the centroid of the overall section is here, and I'll label that as the big X axis. Though if we were to scroll up a little bit, you could see that that same axis right here in the original sketch is labeled NA. And so I think that the authors of the textbook that I poached this problem from are referring to that as the neutral axis, but I'll refer to it in section as the x-axis. Then I'll also refer to that as the y-axis that comes down through there. So the z-axis would be coming out of the plane of the page at us, and it would be along the axis of the member. So the first thing that I'll do is calculate the moment of inertia of the cross section. So I'll break it down into three sub areas. So the top flange, the top flange is going to be sub area number 1. The web is going to be sub area number 2, and the bottom flange will be sub area number 3. Now each of these primitive shapes has a centroid. The centroid for shape number 1 is right there. For shape number 3 is right there. For shape number 2, it's right on top of the centroid for the overall section. So what I'll do now is I'll go ahead and sketch in these axes for the sub areas for the sub shapes. And so this is going to be axis X1. This is going to be axis X3, and it works out that axis X2 is right on top of the major X axis. Excuse me. So I can go through now and calculate these moments of inertia. Let's see, I'll work in black. So I could say that I sub big X1 is equal to I of little x1 plus A1 times D1 squared. So the I sub big X1, that's the moment of inertia of shape number 1 about the x-axis. I sub little x1 is the moment of inertia of shape number 1 about the little x1 axis. So we can calculate those, and so I can come in and I can say that that's equal to the base times the height cubed over 12. So the base dimension is 300 millimeters. I'll leave the units off. Times 20 millimeters is the height cubed divided by 12. And then we add in AD squared, so the area there is 300 millimeters multiplied by 20 millimeters, and then multiplied by the distance, and that distance D1 is this distance right here. And so that's going to be equal to, let's see, it's going to be 100 millimeters to that point plus another, so it's going to be 100 and, whoops, can't possibly have the wrong color in there. So that's going to be 110 millimeters, and then that's cubed. And if we push the number here, then what we get is 72.8 times 10 to the 6th units of millimeters to the 4th. Okay, we can do the same thing for area number 2. In this case, it's going to be equal to the base, which is 15, times the height. The height is 200 cubed divided by 12 plus some area times the distance 0 squared. So I don't care what the area is, since the distance is 0. Then that number works out to be 10 times 10 to the 6th millimeters to the 4th. And then, oops, that was I sub x2. And then finally, I sub x3, by virtue of symmetry, is the same as I sub x1. That's 72.8 times 10 to the positive 6th millimeters 4th. So if we add those together, we get the overall moment of inertia I sub x for the entire section about the big x axis, and that works out to be 155.6 times 10 to the 6th millimeters to the 4th. All right, now there is a shortcut that could be used here, and I won't go through the time to work that problem out here, but if you're interested in boning up a little bit on your moment of inertia stuff, then you could take a look at that. If you go to the PDF solution to this problem, then that is presented here. So the first part of this is basically just a rehash of what I just talked about, and then the second half is the shortcut, where you can actually take the positive area of an overall larger rectangle like this and then subtract off two negative areas, and you end up with the finished product. And it's not behaving that well, but that's okay. All right, so take a look at that on the PDF if you want to review that. All right. Okay, our next step is to consult our equation sheet, and I have that superimposed here on the right. And if we look at the equations that we have available for bending stress, we have the familiar form of the equation sigma is equal to m times y divided by I. So if we write that in over here, then we get that sigma is equal to m times y divided by I, and we'll retain the negative sign for sake of completeness. Now this is going to be the moment, it's going to be the stress sigma in the z direction as a function of the moment that is acting about the x-axis, and thus we need the moment of inertia about the x-axis as well. So when I'm looking for the stress in the top flange, then I'll go ahead and I'll put in y for the top flange of 120 millimeters. When I'm looking at y for the bottom of the top flange, I'll put in 100 millimeters. If I'm looking for the stress at the top of the bottom flange, I'll put in a value of y equals minus 100. And for the stress at the bottom of the bottom flange, I would put in a value of y equals minus 120 millimeters. So let's go ahead and calculate the some stresses here. Calculate the stress at the top of the top flange. And for that, we get sigma in the z direction is equal to minus m, and m is 260 kilonewton meters. And the Y value that we'll use here is a positive 120 millimeters for the top of the top flange. Then we would have our value of I. So this is 155.6 times 10 to the 6th millimeters to the 4th. And if we go ahead and push the correct numbers through here, then what we end up with is a value of 200.5 megapascals, and it's negative, of course. Now, in working through these calculations, if we work in units of kilonewtons and millimeters, then we end up with our result in gigapascals. So when I type this into my calculator, I type in 260,000 kilonewton millimeters, and then the result that I get is minus 0.2005 gigapascals. Excuse me. So then I make that conversion to move the decimal place to get megapascals. All right, and then let's suppose that we wanted to calculate the stress at the bottom of the top flange. Then the calculation would be sigma sub z is equal to minus 260 kilonewton meters times a positive 100 millimeters divided by I of 155.6 times 10 to the 6th millimeters to the 4th, and this is equal to a minus 167. Where did that number go? There it is, minus 167.1 megapascals. We could do the same thing at the bottom flange. If we just plug in a value of negative 100 millimeters, get a positive 167, or plug in a negative 120 millimeters and get a positive 200 megapascals. One side note here is that when you convert the moment of inertia from millimeter units to meter units, you have to be careful. So if we were converting this, we could say that I sub x is equal to 155.6 times 10 to the 6th millimeters to the 4th. But if we're converting this to meters, then we would have to say that there's 1 meter in every 1,000 millimeters, but then this has to be to the 4th. So then this would actually go to 155.6 times 10 to the negative 6th meters to the 4th. So when you convert the moment of inertia in SI units, you have to be careful about that. It actually moves 12 decimal places when you make that conversion from millimeters to the 4th to meters to the 4th. All right, let's scroll down here a little bit. I have an elevation view prepared of the cross section, and I want to plot the stress distribution on the cross section. So I have a ruler in my hand. I'll take a scale of 1 square is equal to 50 megapascal. So at the top we have 50, 100, 150, 200. So this is going to be 200 megapascals. Stress should be 0 at the neutral axis. We get 200 megapascals at the bottom flange, and it's a linear distribution of stress as long as we haven't yielded any of the material in the cross section. So this is 200.5 megapascals in compression. This is 200 megapascals in tension, and I would go ahead and sketch in the stress vectors like that, just to make it look a little bit prettier. So that is a distribution of stress on the cross section. Okay, so what I'll do is scroll down a little bit more here where I have prepared a 3D sketch, and this comes out of the PDF solution to the problem. So this is the top flange here. I'll reinforce that line a little bit, that line, that line. And you can see that it has a flange width or a flange breadth of 300 millimeters, a flange thickness of 200 millimeters. The web isn't shown here, but I'll go ahead and sketch that in as well. So that web will go from here over to about here, say, and at some point down here we'll have our neutral axis, our x-axis, and it will go if I draw it parallel to that top flange, about like that. So that's the x-axis. And then this is the y-axis coming up like that. So I've shown in this distribution of stress, and this is the same distribution of stress that we just sketched from the side view, or the elevation view of that girder. It's just that in 3 dimensions, it has a 3-dimensional nature to it. A lot of people refer to it as a stress block, but really it's a wedge. It's not really a block because a block is rectangular and this has a triangular element to it. So that's what it looks like in 3 dimensions. And if we were to take it down into the web, then it would be down like that into the web. And I probably don't have the skills that I need in order to sketch that. It doesn't suck, but it could be a lot better. All right, so what I want to do though is I want to take this discussion and I want to zoom in a little bit here. I'm going to draw a differential stress block here on the face of that surface. We'll call that dA. And on that differential stress block is some stress that's acting there. And we could calculate that. We know what it is. Sigma is equal to m times y over I, so that is sigma. And if we take the stress acting over that differential stress block, that stress block is small enough that the stress is roughly uniform, even though that we know that it is in actuality linearly distributed. So we can have some differential force here, dF. Let me zoom back out now. Now what we can say is that that differential amount of force, dF, is equal to sigma times that differential area, dA. And now if we look at the axis of that force, relative to the neutral axis, there is a distance there, d, or we could say that that's equal to y, because we're measuring it from the z-axis. And then we could say that there's some moment created by that force, df, and we could say that dm is equal to df times that distance d, which is really the dimension y. And then if we could expand this a little bit, we could say that the differential contribution to moment is really equal to sigma times dA times y. And if we integrate that, let me come down here, we could say that the moment acting on the section is equal to the integral over the area of dm. That's equal to the integral over the area of sigma times y. Whoops, I wrote that wrong. It's equal to sigma times y times dA. All right, now let me take that and then we'll scroll down a little bit more where I have the same image, but now I've just got it drawn in cross-section instead. So it's a sectional view here. And what I'm going to do is start off with that same equation that I just wrote, that the moment is equal to the integral over the area of sigma times y times dA. So what is that area dA? So let me draw in green here. Since the stress sigma is not a function of the x direction, we could take that differential area dA as a strip or a stripe of area across the width of the flange. So this could be that area dA. And that could be equal to the breadth of the flange, b sub f, times dy. Now what are those two terms? Well, the breadth of the flange is this dimension here. I probably should have chosen the location of my dimensions a little bit more carefully, but I did not. So that is the dimension b sub f. It comes from the idea that that is the breadth of the flange or the width of the flange. And then, of course, the distance dy, as you are most likely familiar, is going to be this dimension here. So we could go in and we could say that the moment that's carried by the cross-section is equal to the integral. Let's see, we'll take it from the bottom, minus 120 millimeters, to the top, plus 120 millimeters. And that's times sigma, which is minus m times y divided by I times y times dA, which we now learned is b sub f times dy. Now, I should note that this value of b sub f actually changes if we're in the web of the cross-section. then that wouldn't be B sub F anymore. That would actually be T sub W, the thickness of the web. So that would be T sub W for Y equals minus 100 to 100. But it turns out that I'm not interested in that, really. What I'm interested in is this, that I'm interested in the moment that's carried by the flanges. So we could say the moment that's carried by the flanges is equal to the integral from minus 120 to minus 100 of minus m times y squared over I times b sub f dy plus the integral from positive 100 to positive 120 of minus m times y squared over I times b sub f times dy. So it works out that this is the moment carried by the bottom flange, and this is the moment carried by the top flange. And through virtue of symmetry, we could say that the moment due to carried by both flanges is equal to 2 times the moment carried by one of the flanges. So we'll say 2 times the moment carried by the top flange. So that's integral from 100 millimeters to 120 millimeters of minus m times y squared over I times b sub f times dy. All right, let me scroll down a little bit and give myself some more space to work with. Oops, not that much space. There we go. All right, so if I do my integration here, the moment comes out. So we could say that m flanges is equal to, the moment comes out, so minus m, b sub f comes out, I comes out. None of those are functions of y. There's also a 2 in here, so let me erase that. I'll put minus 2, bring that line over, and then this is times the integral from 100 to 120 of y squared times dy. So this is equal to minus 2 times, let's see, I'll just keep it in terms of the variables now, and then we evaluate y cubed over 3 from 100 to 120, like that. So then we could go ahead and plug in our values, and what we would end up with is minus 2 times 260, I'll go ahead and write it like this, kilonewton millimeters, times b sub f, which was 300 millimeters, like that. I'll use my ruler in an attempt to make this less bad. This is 155.6 times 10 to the 6th millimeters to the 4th. And then here we have 120 millimeters cubed divided by 3 minus 100 millimeters cubed divided by 3. And then ultimately we end up with the final answer, which is equal to and if we work through the units as well, it works out to be 243.3 kilonewton meters. So after going through all of that calculus, then what we could say is that the ratio of the moments carried by the flanges to the overall is 243.3 kilonewton meters divided by the total moment, 260 kilonewton meters, is equal to 93.58 or 93.6%. So the flanges carry more than 90% of the bending moment that's applied to the cross section, and the web doesn't carry very much bending moment. And the reason for that is that it's because the flanges are further away from the neutral axis. So the flanges, being further away from the neutral axis, have a larger moment arm to carry a larger percentage of the moment. Now the web isn't there for nothing. It's there to keep the flanges in place, first of all, and then later in the semester we'll come back and rework this problem when we're talking about shear, and we'll figure out that the flanges carry most of the bending moment and the web carries most of the shear force. All right, now There's a little bit more to this problem in the version that's posted as the PDF. If we were to look at that, I've gone through and I've calculated the moment that's carried by the flanges by looking at the stress block that's in the flanges. So we could represent this stress block here, and we could say that there's one force resultant that acts at that stress block there that passes through the centroid of that stress block, take the moment that's created by that, and that is the moment that is contributed by the flange. So there's just one little hiccup, though. You might want to say that concentrated force F, we'll call it F sub flange. I don't know if it'll let me put it in here. That's equal to the volume of that stress block, but the centroid isn't right at the center. The centroid isn't at, say, 10 inches from the top of the flange. Because there's this triangle contribution here, it means that the centroid is just a little bit higher than the center of that flange. So when you look through these calculations, you can see how I've calculated that centroid and then figured out where that force acts, and then I take that moment. So take some time and work through that on your own, and you'll be a better person in the end. All right, I hope that this all helps.